All right, so today we're going to start chapter one, measurement and calculations. We really won't do a whole lot in this chapter that we would consider chemistry, but we're going to learn a lot of rules and review a lot of rules that we'll use to handle data and calculations throughout the course. So the first thing we want to talk about are the two major types of data that we have. The first and by far most common type is quantitative data. So quantitative data, as you could probably guess, in some way deals with a number. So for a piece of data to be considered quantitative, there has to be some kind of numerical component to it. And for it to be considered a measurement, we have to have some sort of numerical component as well as some sort of unit. So something like 12 meters or 14 grams. And these are by far the most common types of data that we'll deal with. But the other type of data that we will see sometimes is called qualitative data. So qualitative data is anything that basically doesn't involve a quantity. So something we could describe as a color. So we could say after the reaction, the copper was blue, for example. Or we could even have a qualitative piece of data, something like the temperature increased. Okay? Or we could use that same piece of data and make it quantitative and say the temperature increased by 14 degrees Celsius. So two words that we're going to use to describe the data that we have, mainly the quantitative data that we have, are accuracy and precision. So you have the definitions typed out there for you. So accuracy is basically how close an instrument can get us to the correct value, or the true value, we'll call it. And precision is a measure of how repeatable the value is able to be attained each time. So let's look at it in terms of a graphic here. So let's look at a little bullseye. So let's just say X is the target that I'm trying to hit. So let's look at the left one first. Let's say I shoot some arrows and these are the spots that I hit. So I shoot a bunch of arrows. They're kind of spread out, but they're all very close to the bullseye that I'm trying to hit. So over here on the right, let's say I shoot some arrows and that's where they hit. So you can see that they all hit almost the exact same spot, but it's nowhere near the target. So we could describe this set of data over here, we could say that it's pretty accurate, because all the arrows are close to the target or the true value in terms of data. But on the right, we could say this data is precise, because all the arrows hit fairly close together, but they're not necessarily accurate because they're not near the target. So let's look at it in terms of data now, because obviously we won't be dealing with a lot of target practice in chemistry. So let's say I have an object and I know that it weighs 5.00 grams. Okay? Then let's say I have 4 students and each of them weigh the object using some method they come up with 4 times. So let's say student 1 decides that, or rather reads their measurements as being 5.01 grams, 4.99 grams, 4.98 grams, and then we'll say 5.02 grams. Okay, so that's the data they record. After they weighed it, they decided, okay, these are the 4 measurements that I came up with. So let me spread this out a little more. So then let's say student 2 comes in and their measurements are 7.00 grams, 6.00 grams, 4.00 grams, and 3.00 grams. So student 3 might measure whatever this object is as weighing 1.23 grams, 1.22 grams, 1.23 grams, and 1.24 grams. And then student 4 may come in and they record these measurements: 7.42 grams, 14.78 grams, 9.64 grams, and 11.98 grams. So now we need to use the terms accurate and precise, or rather we can describe the accuracy and precision of each of these four students and their measurement. So let's start with student one. If you look at student one, all their measurements are grouped very close together. So we can say that this student is precise. And we can see that their measurements are all very close to the true value, or the known value. So we could say they're also accurate. Okay, if we look at student two, as compared to student one, they're not very precise. Their measurements are pretty scattered out. So we can say not precise. But if you were to average out those measurements, you would see they're actually pretty close to the known value. So we could say they are accurate. Then if we look at student three, all their values are pretty close together. So we could say they're precise. But their values are not close to the known value. So we would say they are not accurate. Then student four, they're kind of all over the place. Their values are not close together, so we would say they are not precise. And then their values are not close to the true value, so we would also say they are not accurate. So those are the four combinations that we can have for the terms accuracy and precision. So obviously, our goal is to record measurements that are both accurate and precise, but you'll see that different combinations of those terms occur quite often. So those are the two terms that we'll use to describe kind of the quality of our data. So how good is the data we recorded? So we need some way to convey to others the quality of our data. So what we use to convey that to others is known as significant digits. And I'll abbreviate that SD, or we call it significant figures quite a bit. So I can abbreviate it SF. So significant digits and significant figures are terms that are used interchangeably, and I'll probably say both quite a bit. So significant figures are the number of digits that meaningfully contribute to the accuracy of a measurement. So that definition probably doesn't tell you a whole lot, the number of digits that meaningfully contribute to the accuracy of a measurement. So let's think about what that really means. So let's use a sports example here. Let's say you go out on the football field and you throw a football 10 yards, for example. That's as far as you can throw it. So you could tell your friends that you threw the football 10 yards because the football is striped off in 1 yard increments. Or you could tell your friends that you threw the football 10.12789 yards. The second number isn't necessarily a lie on your part. You could have very well thrown the football 10.12789 yards, but you really have no way of showing that. And so we need some way of relaying to others that, well, we know this 10's accurate. I know I threw it 10 yards, but I really kind of just made up the rest of this. It's really just an estimate. So in order to do that, we use significant figures. So first we're going to talk about how we actually measure significant figures when we use equipment, and then we'll talk about more what they actually mean and how to deal with them in just a minute. So another more usable definition of significant digits or significant figures, the way I abbreviated it, is that they are all known digits in a measurement plus one estimated digit. So what that means is I could write something like 15.4 grams. So you're always going to estimate the smallest digit. So that's saying I'm estimating the 0.4, but I know the 15 is accurate. I'm confident in that. Or I can have something like 12.001 milliliters. So what this measurement tells us is that I'm confident about the 12.00, but I'm estimating the ones or the thousandths place right there. I'm estimating that value of that one. So from this point forward in the class, whenever we have a measurement, we're always going to know that one of the digits was estimated and the rest are known. And we call those the significant digits. So in this case, for example, let's go back to this number right here, 12.001498, for example. Let's say that was my original value. And I knew with pretty good certainty that this part was accurate, the 12.00. And then I estimate that number right there. So then at that point, we leave off these numbers. Because if we're estimating this place right here, why would we go and estimate another place? So let's look at an example that's easier to see that. Let's look at 274. Let's just make up a number. We'll say grams. So let's say I know this digit is accurate. Okay, I know the hundredth place is in fact should be a 2. Then I'm estimating the 10th place as 7. So that means I'm not really sure about that. I'm estimating, so it could be 270, it could be 280, it could be 260. So if I'm estimating this place, why would I estimate another place? So if it could be 260, 270, 280, why would I say that it could be 274? There's no point in estimating smaller and smaller numbers there. So I would simply write that as 270 grams. So now that tells me I'm confident that the 200 is correct, and I'm estimating that the 70 is correct. So when we record data, it's our responsibility to ensure that we record all the known digits of a measurement plus one estimated digit. So for our digital equipment, such as the balances in the lab or digital thermometers, the equipment does that for us. So if the digital balance reads 14.012 grams, that's what we record. The balance is telling us that is accurate, the 14.01 is accurate, and the 2 is the estimated significant digit. But when we have non-digital equipment, like a ruler, a graduated cylinder, something like that, it's our responsibility to record the correct number of significant digits. So look at the first image in your notes. You have a thermometer. So on that thermometer, it is measured off in increments of 1. So if it's measured off in increments of 1, we can be confident that the temperature is 82 because it's divided off into those numbers. So I know it's 82, and then I'm going to estimate that it's 82.5. And because this 0.5 is an estimate, yours could be different than mine there. And then the units were cut off just degrees Celsius. So if I look at the second image, I know that the temperature is 35 because that's what the thermometer is divided up into. And then I'm going to estimate it's 35.0. Could you also say that it's 35.1? That's what you think it is. That's perfectly valid, okay? Everyone's last number can always differ because the last number is always an estimate. So then in the last image of the graduated cylinder, I can be sure that 6.8 is accurate because the graduated cylinder is divided off into increments of tenths. Then I'm going to estimate that the proper measurement is 6.83 milliliters. Could you have also said that it's 6.82 and be perfectly correct? Yes, because that last place is always an estimate. So again, be sure that you remember that it's always your responsibility when you read equipment that's not digital to record all the numbers that we're sure of, plus always estimate one more number there.